Okay, so yeah, so let's start. And I think it is better to change the. Uh, can you hear me? Okay. So I think last time we had some problems that are not. Uh, I think last time we had some problems that are not solved yet. And I think the first is to concern about the Riemann surface. So let sigma g uh, a Riemann surface. I think we should not emphasize the Riemannian matrix G, but the almost complex structure J. So let it be a Riemann surface with almost complex structure G, almost complex structure J. And we know that an almost complex structure is automatically a complex structure. And last time we say there is a volume, we fix the volume form on sigma. And we know that the volume form in complex geometry setting, the volume form serves as a Taylor form, or to say the image part of the imagined part of the emission of some emission inner product omega, which is a 1-1 form. So in this case, we know that the volume form induces a Riemannian matrix G on sigma, which is defined as Gxy is equal to the volume form acting on X and Jy. Maybe we have to let J be or J. Maybe you have to let J be Jx and Y. At least it is Jxy or the volume form of X and Jy. They differ from a sign. So one of them is positive definite and another is negative definite. I think this is positive definite. So a volume form will induce the natural emission inner product or the emission structure. And so we can, with volume form, we can always have the hot star operator. And there is another problem concerning about the emission structure. We say emission structure is a real product. The emission structure G is a uh, no, uh, let's say it's a bilinear form such that it is Gx is emission. No, Gx is inner product, an inner product, and is compactable I think this should be a vector bundle, and the emission structure over some vector bundle, it maps onto the trivial bundle R. Is an inner product that is compatible with the almost complex structure C. This is one definition, and another definition is to say it is just a emission inner product. And they are equivalent to, and an emission connection is something that we can define it as, first of all, we can define it as the connection satisfying the Leibniz law, that is plus h and x del x nabla y, and also we can define it as a Levi-Civita connection with an additional assumption that it is bilinear. They are equivalent because we have a natural relation between these two. That is, first of all, we can have H. If H is a emission inner product, then we can set G is the real part of H, and we know that H can be written as the real part plus I times the image part of H, and we know that and it should be compatible with the almost complex structure J. So we have H of Jx y equals to the real part of H and Jx y plus I times the image part of H and Jx of y. But we know that Hj of y is equal to I times H of x and y. So we know that this is equal to I times the real part and minus the image part. So this tells us the exact relationship, that is the real part is equal to minus the image part of xy and the image part of h xy equals to I times the real equals to the real part. There is J, real part of h and x and y, and we know that the imagined part is the Taylor form omega, which is a 1 form of sigma. So we know that there is an so we know from the we know also the answer to 1 because the volume form serves as the Taylor form, and we know that the emission in the given Riemannian matrix is given by the exact formula, and this is down here. Yeah. So we know that, and with some additional with some more calculation, we know that they are equivalent. That is, it satisfies the Leibniz law with respect to the emission inner product is equivalent. So it is a Levi-Civita connection, and the connection is bilinear. I have written down the exact proof. I have written down the proof on the seminar webpage on Appendix A, and the first one is about the equivalence between these emission connections, the definition of emission connection. Okay, so now we going to introduce the generalized Riemann-Roch theorem and also the corresponding cell duality. So last time we have introduced the real linear Cauchy-Riemann operator, and there is something more to mention. Yes. So we say that a real linear Cauchy-Riemann operator of class Wk minus 1p, we must impose the we must impose the condition that Kp must greater than 2 because of the Sobolev embedding theorem. And we write ds to be the restriction of the real linear Cauchy-Riemann operator of class Wk minus 1 and p to the subspace of all sections of E with of class W of Kp. Yes, we need the section to be continuous. Otherwise, it does not quite make sense for us to say a section which is not continuous and is only of class LP, or less it is only a distribution. It does not make sense because I think when we do not have the continuity, we will have so not continuity. Then this space is not compatible with the coordinate change. So when we make a coordinate change, then the space would would change sharply. So this here we must impose the continuity. But the sections, but the vector field can have weaker regularity. Yeah, because we also need the boundary condition. Okay, so now we want to say about the joint operators. That is, we have operator df, then we want a corresponding operator df star. And we need it to be a joint operator, or to say a formal adjoint operator to df. In this case, we need so let C is in omega of 0 and sigma with values on bundle pairs, and eta is only one form of a 0-1 form over the bundle pair ES. Then we say the adjoint operator. We say something is a joint operator. It's a joint to df means that with respect to some emission inner products, we have first of all we add df on C and on eta, and minus what happened? And minus the operator of the C and the operator acts on the joint operator acts on eta. It should be the uh, it should be it should then be integration on the boundary. So the integration is given by sum is given by I think this should be so something. It should equal to sigma, and it is linear in it is linear in both sections, and with some orders of derivatives, and this should be first order. So they are just linear combinations of the C and eta. They're linear, so we can write it as okay. Yes. So this is the formula for the joint operator. Because we have a boundary, so we need because we have boundary, so it is not the exact. So we cannot always achieve the exact identity. That is, we cannot achieve that should be 0. But in this case, we can achieve this. So this is a proposition. That is, if the C and eta belongs to have the corresponding boundary conditions, then we will have the integration of the C and df star eta integrate with volume form is equal to the integration over df the C pairing with eta. So, and this formula is proved in appendix. The proof means that for any given formal adjoint operator, for any given differential operator, there would exist a formal adjoint with some boundary conditions. Without any boundary conditions, then we will get an arbitrary form G. But with a given boundary condition, then we will have some more things. We will have some more things. So we can have this is an identity. So so the proof only treats with the boundary conditions. That is, if it is the integration over the boundary is a formal combination of the C and eta, and integrate on the boundary. So it is, I think it is integration over the line, so we can say it is integrated over df. But we know that the integration is just let's see, which star df star eta. minus df star eta, df star df c wedge star eta. We use the Hodge star operator to realize the joint operator, and then we obtain that it should be, so df star is something which df star is should equal to star df star, and with some sign, the sign should be minus. Okay, and so we will get a formula. It is yes, and this will equal to df no, the whole b epsilon the c wedge star eta, because it comes from Hodge star operator. So we have no, it is no uh, so it is equal to this, because the c is zero form, and no, okay, so we should make some, okay. The formula, we should change the role of beta in the C. So let's no difference. So this comes from the Leibniz rule, and oh, here. There is some let me say again. So there is some formulas for df star, so we can change. So we can have the integration to be like there should be some formulas for the yes. So if we have a real linear Cauchy-Riemann operator, and we don't, huh? What happened? Okay. So if df is smooth, then we know that df comes from some del bar operator. Then we have so df star is just we impose the boundary condition f. So df star is just the del bar star. And since it is a del bar operator, we have the corresponding Cauchy-Riemann. We have the corresponding Leibniz rule. So if we calculate the difference del f connection star eta and c, the volume form sigma minus the eta and del f connection c is equal to the integration, and we have this is just the this is just the real part of the this is just a real part of the of this Hodge-star operator, and so it is a real part of uh, the C, which star and the DLF connection star eta minus the real part of the C, which DF del F connection to C, which star eta. But we know that we have the corresponding formula, so that is the real part of H of xy and plus the image part of H times I, and but the image part of H is equal to the real part of H. No, it is in the minus of the real part of H, and the Jx and Y equals to the whole H. This tells us that the real part of H can be expressed as no. This tells us that H can be expressed as yes, the real part of H can be expressed as some terms of expressed as something some terms of H in terms of H, that is uh, uh, so on the other hand, we have the real part of H as Jx and Y plus I. The image part of H of Jx and Y is just the real part of H and Xy equals to I times H Xy. So this is the same, there is no difference. So the thing is equals to Hxy plus I times the real part of H and Jx and Y. And in this case, we have so we expand the del H to obtain to see which del F connection del bar. Here is the del bar F connection of eta minus the real part of del bar F connection to C, which star eta. So we know that it is just a real part of the C, which del bar eta minus del F connection to C, which star eta. So it equals to the real part of del connection of the C, which eta. So we know that this is the 0, 1 part of some connection. Nabla. Uh, and we know that it has an explicit formula like del nabla minus j nabla j the small j. This is plus or minus. It is should be uh, it should be plus. So with j and it is plus. So then we obtain real part of d and plus j times j times of j times this. No, there should be. No. I made a mistake. So uh, no. Okay. Okay, that is okay. So but we know that this is a 0, 1 part of the connection, and star eta is in fact belongs to A10 of sigma e. So this tells us that the C wedge the wedge this string must belongs to this, and so d of the C wedge star eta is equal to del bar of the C wedge star eta. And when we impose the connection, then this will become the connection of C wedge. I think they are the same. No, they are not the same. But we know that it is yes. So we have Stokes formula to change it into integration over the boundary. So I still don't understand why there is a change. But the thing is that on the boundary we have the integration must be the pairing of the C and J eta, and they are all real. Real means that Jf is orthogonal to F, and this tells us that this should be identically zero. So we know that the integration should be equal. Here we have here it is here it is here this is the real linear of class W k minus 1p, and we know that this is only differ by adding one form of class W k minus 1p, and its adjoint can be written directly as just the adjoint matrix to A. And we know that in this case, we have already must identically equal to A star uh, to 3 times A star eta. So we know that in this case, the things are the same. We do not need to change anything, and so we done the proof. And now we are going to state the main theorem, that is the generalized Riemann-Roch theorem. We are concerning the pairing of df and its, we are concerning two things. One is df and the second is its adjoint operator. So we have ef a bundle pair and df the real linear CR operator of class W minus 1p. And in this case, L minus 1p. And in this case, we have another integer k belongs to 1, 2, L, and also another positive real number q greater than 1 such that k minus q over 2 is not greater than is less than or equal to L minus p 2 over p. This condition is used to impose that the smoothness is not always achieved. That is, since the coefficients are not smooth, we cannot require the whole solution to be smooth. So it is only has some kind of regularity. And we know that df from W kq f of sigma e to W of k minus 1q of the one form and its adjoint operator df star from W k minus 1q of kq f sigma, which the 0, 1 form with values in E to W of k minus 1q and sigma E of Fredholm operators. That is, it has a finite dimensional kernel and finite dimensional co-kernel. So we have a well-defined Fredholm index. And moreover, kernels are independent of k and q. It is reasonable because the regularity is not the obstruction to the space of solutions because they are always assumed to be smooth. And we have, but here the coefficients are not smooth, so we cannot require the whole solution to be smooth, but they should be as smooth as possible. And we have the following adjoint relation. This means that if eta is this means that since eta belongs to the image of df, then we can say that the kernel of TF star is orthogonal to the image of TF. Because the space is Sobolev, so we have because the space is Banach, and another thing is about the kernel, or to say it's about the dual of. So if the C is in the image of TF, then we should have the integration of the C. So the C should be on the other side. Yeah, the C0 and the C, and integrate over the volume form with 0 for all the C0, which belongs to the kernel of TF. This means that the kernel of TF is in fact orthogonal to the image of TF star. And we know that and we know that for the C in W of K minus 1 Q of sigma and E. And the second one is about the Fredholm index. Of TF, it should equal to the sum of some topological invariants. The first is the overall characteristic of sigma times n. N is the rank of E. And we plus the topological invariant of the bundle pair EF, which is the relative first-term class, or to say the boundary Maslov index. In practice, we always cancel the first term and remain the second term. In order to cancel the first term, we know that like sigma is a cylinder. Then we have the all characteristic is 0, because we know that the cylinder is homotopy equivalent to S1, and S1 has only one-dimensional H0 and one-dimensional H1. Then the Betty number, then the sum of then the alternating sum of the Betty number should be identical to 0. So we have the all characteristic 0, and so in any case, the index is equal to the Maslov number. On the other hand, it is the space of dimension, and it is the dimension of the cylinder is the flow trajectory. And we then obtain the explicit formula for the dimension of moduli spaces. On the other hand, mu EF is equal to 2C1 of E if F is empty. No, if sigma, if the boundary is empty. So we know that this is twice the first-term class of the vector bundle. And in this case, we know that so it is real linear. That means that the dimension, the operator is real linear, means that the dimension is twice the complex dimension. So in fact, if TF is complex linear, then we have Then we have the complex dimension. Then we have the index for complex dimension. That is, if this is bilinear, that is, this is complex. Then the operator, the index can be counted with complex dimension. No, the index cannot be counted with complex dimension. Yes, so it should be 2 over n and plus 2 and plus the C1 of E. Its sigma has no boundary. And you know that this is very close to the classical formula, where we replace the C1E by the degree of the line bundle L or the divisor D, and this will be 1 minus G. And we know that the relation between the Riemann surface, the genus G, and the Euler characteristic. That is, the Euler characteristic is always equal to the G. No, it's always equal to 2G minus 2 or 2 minus 2G, 2 minus 2G. For the real Euler characteristic. The complex means that we use the double cohomology, and the real means that we just use the ordinary cohomology. So the dimension is just 2 minus 2G, and we divide it by half, then it should be 1 minus G. So the classical formula shows 1 minus G plus degree D equals the index of the Riemann operator. And in that case, df is just del bar. So this tells us that the index is just the dimension of L of D, that is the space of all holomorphic sections over D, and minus the dimension of Lk minus D. The other is about the cokernel of df. But we know that the cokernel of df is isomorphic to the kernel of df by the above formula, that is the image that is here. Because we know that the cokernel of df and cokernel of df star are also finite dimensional, so we know the cokernel derived from the kernel is the whole space X. And we know that the kernel of df star is orthogonal to the image of df, and we know that the kernel of df star is lies in the WKQ of something. And this is contained in WK minus 1Q of something. And so in this case, the orthogonal, they are orthogonal means that we can also derive some with df star. They are finite dimensional, and there is bijection. So this would be an isomorphism. So we know that the tool is isomorphic, and so it is also no. So we know that it is also the kernel of df star. Df star is also a Cauchy-Riemann operator. It's a joint of some Cauchy-Riemann operator. And by some more calculation, we know that this is just equal to the dimension of Lk minus D. So here we obtain the classical formula. And we have more things. The third one is also a classical result that if mu of EF is less than 0, then this implies that DF is injective. And in classical setting, this means that if the degree of the divisor is negative, then there is no global sessions of the sheaf LD. And if the and if and if the topological index is sufficiently large, then DF is surjective. And this corresponds to the fact that the degree of Kx is 2G minus 2. That is the canonical divisor. If 2G minus 2, then this implies that the dimension of H of L, oh no, Lk minus C is 0. That is, there are no, the dual of the line bundle has no global section. And we also have n equals 1, the condition. Okay. And this is a statement of the main theorem that we are going to prove. So after introducing cell duality, then we will go into the proof of this. There will be a long walk because we have to do the Fredholm property, and then we have to calculate the Fredholm index, and the index is related to some topological invariant. We should introduce especially the boundary multiple index, which do not appear in any other context. And then we have to prove the special cases. Okay, so then we go into cell duality. The cell duality says that there is some isomorphism between one homology group with another, and we know that they are closely related to the Riemann-Roch theorem, and we always use the Riemann-Roch theorem to prove the cell duality. And here we just do the same thing, but we will do some more things, like so cell duality concerns with the holomorphic. So first, let's make a remark. A remark is that if sigma is a Riemann surface, then any Cauchy-Riemann operator gives an holomorphic structure on E. That is, if we have a complex smooth Cauchy-Riemann operator over some vector bundle E, then we automatically give a holomorphic structure on E. So E is automatically a holomorphic vector bundle, and we know that. So this can be this is in Kobayashi. So this tells us that, but in general, let's make a remark. In general, we must have the complex smooth Cauchy-Riemann operator. In general, CR operator has an additional condition or requirement that del bar square should be 0. But this is always automatically true in the over the Riemann surface. So any vector bundle over some Riemann surface are automatically holomorphic, and one Cauchy-Riemann operator gives one holomorphic structure over E. And in this case, we have also and then any CR operator over some complex manifold over some complex vector bundle E over some complex manifold X will give E a holomorphic structure. And they are in fact equivalent. That is, any holomorphic structure also gives a unique Cauchy-Riemann operator over the vector bundle. So we can just fix a holomorphic structure over E on E. And the set duality concerns the things on cohomology. So we must define the similar concept for dual. We must form the similar concept for the actual for the dual bundles and what happened? Oh no, okay. And fix almost structural E, and we must say in the line bundle setting we just have OD and the corresponding dual bundle is O minus D. But here we don't have the group structure, so we have a dual bundle E star, and we consider the corresponding bundle of corresponding 1-0 forms over the dual bundle E star. We know that E star is automatically a complex vector bundle with with almost complex structure J, and the Jx just like J mu of S on S is mu of S on Jx, like that, and we know that if F is a totally real subbundle of E on the boundary, then F star, which is the base of all linear functions such as mu composed with E composed with S is mu maps the whole subbundle into Fj. That is, it is a real function. No, it is real function. Is a totally real subbundle of E star restricted to the boundary. And we know that for the tangent bundle of sigma, the C-linear the C-linear dual bundle is just isomorphic to the 1-0 form of sigma, and antilinear is another. So in this case, we can form the bundle of differential forms as a section of the we can form the bundle differential 10 forms over E star as some dual bundles over the and also we have over the boundary we have like F star is isomorphic to 10 sigma tensor with F star, and they are restricted to the boundary. And this is a totally real subbundle of E star tensor with the 10 form. So this gives us a pairing. The pairing is given by so we have 10 form tensor with E star, and we have another one is the 101 forms on E, and they pair to give a function to give a bilinear function over C, like that is this is mu tensor with alpha, and another is theta tensor with S. Theta is a 10 form, and they will be mapped to and they will be mapped to the integration over sigma, where alpha wedge beta it is a smooth function, and then mu times S it is also another smooth function, and integration over the volume form. This gives the natural pairing, and we have also another pairing that is we have the 0-1 forms of this, and we know that this is in fact the space of all 1-1 forms over sigma E, and so with omega 0 the space of sections to see, and this is just also given by because 1-1 forms like 1-1 forms, and also this is just S, so they will map to the integration over mu S times alpha. I think we don't need the volume form here. Okay. And we know that this is the so-called L2 inner product, and we know that the wedge product is non-degenerate. No, we don't mind if it is degenerate or non-degenerate or not, but we have this gives us an inclusion, omega 0 sigma, not an inclusion, but gives us a map. And so if E star to the dual of, I think we should say it is not the dual of this, it is the dual of L2 sigma and T01 sigma tensor with E, the dual of this. And on the other hand, we have also omega 01 to the dual of L2 sections over E. But they are not the main parts that we are going to introduce, because we already have the Riemann-Roch theorem that states us the finiteness of the kernels and co-kernels, that is the two cohomology groups. So we only need the fact that here we write df as df right as del del bar f to say the canonical Cauchy-Riemann operator. Since we know that this is unique on a holomorphic vector bundle E. Since this is unique, so we can write as just the del bar of S, and we know that then we say any D is just the real linear Cauchy-Riemann operator, just the del bar of S plus some matrix A, and we know that the dual, the adjoint operator, is just the dual with minus sign. And in this case, we know that the integration over D star eta wedge C minus eta wedge B C. Here we here the dual is just map omega 0 of sigma P10 is on the dual operator, is on the dual bundle, and it maps to the 1-1 form with values in the dual bundle. And so we have the easier relationship between these two weapons. Okay, no, nothing. So we have the dual, so we have the corresponding formula for the adjointness. And there is a proposition that says the relationship between these operators. That is, now we say A is of class WL-1P, and LP as defined as in the previous theorem, and we let eta be a LR section on the dual with R greater than 1, and then the following are equivalent. The first one is the integration of eta wedge B to C on sigma is real for any C which is values in the bundle pair. And the second one is that eta is in fact has a great smoothness. It's of class LP, and it is the kernel of D star F or D star, and it is in fact with values in the bundle pair. So the proof uses the Riemann-Roch theorem. Because we know that D and D star are still Cauchy-Riemann operators, and if we know one, then we know that C satisfies the boundary conditions, so this is automatically real. I think with 2 implies 1, it is easier. 2 implies 1 because eta is real, so eta has value in the real. So eta, I think there is something wrong with, no, nothing wrong. So, yes, yeah. We know that C has we know that D star of eta is 0, so this term cancels, and this is real because both eta and C has real boundary conditions, so this is automatically real. So we have proved this, and the converse requires some work. We know that the integration over sigma of this term is real, and this tells us that if we consider the emission inner product, that is, if we consider the emission inner product, that is H, it will decompose into the real part and I times the image part. And so if we consider the image part, then it should be 0. That is because it is real. So this one is this is 0. But the image part of this is just the integration over the emission inner product, and which is minus of. So we can change it into the we just multiply both sides by j, and then this will give us the emission inner product with values in E cancel with one values in the one form, and then integrate over the volume. So we know that this is 0. Since this is 0, so we know this term is 0, and this tells us that eta is in fact belongs to the image of we just apply the Riemann-Roch theorem. Here the integration is for all C in df star of sigma n. In df of sigma n. So for all C in omega fn 0 sigma e. So this tells us that eta is in the image of df. And df, the image of df is just the initiator of the kernel of df star. So this tells us the and it's in LR, it's the LR section. It's in the kernel of df star, so we know that I mean the So because for all C in here, and this is in the image of D, or to say df, and we apply the Riemann-Roch theorem, we know that image of df is orthogonal to the kernel of df star. And we know that eta annihilates the image of df, and so eta will lie in the kernel of df star because the LR is reflexive. No, I mean the space. Yes. If we since we assume the L and P to be sufficiently large, so the kernel is in fact lie in the LR space, and also the image of EF. So, but LR is reflexive. reflexive space, banana space. So we know that eta is in fact lies in the kernel of df star, and this is right in the L R prime. And we know that the the two are dual to each other. So, and this is a reflexive space, and the kernel is a closed subspace. So the annihilator of the image of df is identical to itself. So eta is in fact lying in the kernel of df star, and so this tells us that df star f on eta is 0. It should be D star. We do not know. We do not know if eta satisfies the boundary conditions, but it follows automatically that eta should be smooth as smooth as possible. And we know that yeah, it is as smooth as possible, and we know that it must map the boundary to F. Because it lies in the kernel of D star F. So we have proved the theorem, and the fair duality tells us. So that if we write it down, it is Kp of sigma and T star T10 sigma tensor with E star, and via the dual operator, it will map into Wk minus 1p of sigma and T11 sigma and tensor with E star to 0. This is a new dual operator, which is not the previous operator that we have known. And another one is the ordinary Cauchy-Riemann operator, D bar next to Wk minus 1p and sigma and T01 sigma tensor with E star, E to 0. And we know there is a natural pairing between these two and these two. They cross together, they cross with each other, and we know that the kernel of delta, which is in fact if it is smooth and we work in the space of smooth sections, then this will be H0 of sigma and E star. And with no, it is H0 with double cohomology, H tensor with T10 sigma. No, it is 0, 1. 1, 0. So it is this cohomology, and we know that this is isomorphic to the cokernel of delta, and this is in fact the boundary condition. So we know that this is isomorphic to the H01, the delta cohomology of sigma and E star. It is a dual. So it is a dual. So that is E. And we know that on the other hand, we have del F, and this is in fact a 0 cohomology of sigma and of E star is isomorphic to the dual of cokernel of del star F, the dual. And this is in fact the 1-1 cohomology of E sigma and E star. And this is the so-called fair duality. So we have just obtained somewhat generalization of this, because we do not require it to be smooth. And the general general set duality states that if we have something like uh, the space of four, if we have something like the double cohomology of differential P form, Q forms is isomorphic to n minus P cohomology, double cohomology with omega n minus Q, the set of homomorphic Q forms, n minus Q of most n minus Q forms with values in E, with isomorphic with this dual. And in fact, in many cases, they are finite, so we can drop the dual notation. And that is all of the introductions today. Are there any questions? Okay, so next time we will try to start the proof of the generalized Riemann-Roch theorem, and we will first introduce some notions on partial differential equations like overlap embeddings and something, and then we introduce the elliptic estimate, local estimate for the Cauchy-Riemann operator in order to introduce the global estimate. And the seminar is done today, and see you next Saturday.